Yeah, welcome to this session at Trash Talk, exploring the Java memory management system. So first of all, who's a garbage collector expert here in the room? That's good, because otherwise you would be no more than me. So my name is Gerrit Grunwald. I'm working for Azul. We do JVMs and everything related to Java. I'm also running the Java user group in Münster, and I'm a huge fan of the Dutch Java community because you guys really rock. You have by far the best conferences that I know, and I saw a lot of conferences. So let's start. Memory management in the JVM. It's automatic, right? So why care? Any ideas? Well, it has an impact on the application performance, on the responsiveness of your application, and also on system requirements. And that, I mean, you should be aware of that. And if we take a look at how it's organized, so it just upfront, this is a really dry topic. I try to make it as interesting as possible, so if you fall asleep, it's no problem. So this is how it's structured. So we have the stack, right? The stack frames, and this is per thread. So every time an application opens a thread, it gets a stack frame. And then in this stack frame, we have local access, so it's thread safe, and we only store primitives and references in there. And it's growing and shrinking automatically, so there's no garbage collection in the stack frame. And then we have the heap, which is the interesting part for this session, because this has shared access, so it's not thread safe, and there we have to do garbage collection, right? And it stores objects, the objects that are referenced by the stack frame references here. And then we have the meter space that contains in principle everything that's related to classes for the JVM. We don't want to focus on that. So the main part is the center, the heap. And if we take a look at how it would look with code, I hope it's readable from the back, then you see this little piece of code where we have some records, some persons here, and we have a list of the persons. And if we translate that to the stack frame, then we see we have one stack frame because it's one thread. We have the references for each person and the reference for the list on that stack frame. On the heap, we have the actual objects for each person and for the list. And we see the references pointing from the stack to the heap, okay? That's important. If I now, for example, set the person P1 to null, right? So these are now reachable from the stack. But if I set the P1 to null, then if I would system out print line P1, it's null, right? But it's still not dead, because it's still reachable through the list object. So that means this person object is still live on the heap, even if you set it to null, because there's another reference in the list. This is sometimes what people forget, because it's not really obvious. You think you set the object to null, then it's gone. It's not really. If you have hidden references somewhere in collections especially, they can stick around for a long time in memory. And if I now set the list to null, then, of course, only these three objects are reachable, and the rest, these other objects, is more or less garbage. It's lying around on the heap, it takes space, and so we have to garbage collect it. Right? That's the main idea behind garbage collection. We have to clean up the memory here. So that means garbage collection is a form of automatic memory management. There's also automatic reference counting. This is in other languages, like Swift. Also works, and has also its problems, so garbage collection is not free of problems, as we might know. So it is made to identify and reclaim no longer used memory, ensures efficient memory utilization, and the most important part is it frees the user from managing memory manually. Who did C, C++ in the room? Yes, and you love it, right? malloc and free and all these things related to that. So this is the good part of garbage collection. It should take away all the hassle of memory management from you. And so we separate garbage collection in different phases here. This is only for precise collectors. I don't go into detail because this is not for all. There are so many different collectors. If we talk about precise collectors, then we have 3 different phases. First of all, we have to identify all the live objects on the heap. Remember the ones that have been reachable from the stack. This is the live objects. We have to find them first. This is tracing. Then we have to free the heap from all the objects that are not reachable anymore, so the dead objects, right? This is freeing. That's the second phase. And then we have to compact the heap from time to time. Time to time we will see that. Because you can imagine who worked with Windows 3.11 in the past? Okay. So remember this fragmentation, defragmentation thing? So this is how the heap looks like. So that I will show you in the demo. But to make sure that we always have a lot of free heap available, we have to compact it. This is compaction. So relocate live objects. Okay. We have different kinds of collectors, which is not the garbage collectors that we have in the JVM. This is basic principles of garbage collection. And we start with the easiest one, which is the non-moving collector. And it's mark and sweep. Who heard of mark and sweep here? Yes. And I created a little demo that will show you how it works, because I thought it's way easier to understand if you have an animation. So you see on the right side the different kinds of states that we have. We have free cells, that's the gray ones. Then we have used cells. These are live, it's the blue ones. And then we have the purple ones, they are dereferenced. That's our dead cells, right? So the references are gone, set to null, whatever. And if they have a little red square on the upper left corner, that means they survived, or they are marked for garbage collection. And then if they have a number in there, that just means it survived a garbage collection cycle, right? So if an object is older, this number will increase. So on the left side, you see how it works. We will allocate memory. When we fill up the heap, we will stop the world. We will mark all the live cells. We find them and mark them. And then we will remove all the dead cells, and then we unmark the live cells, and then we continue running. So let's take a look how it works. So you see, objects will be allocated, and they will die. That's the purple stuff. And then once the heap is filled up, we have to stop the world to do the garbage collection. So it's now. And stop, marking, removing, unmark, continue. That's how it works. And you see already what happens, right? We see all these gaps. And then we fill up the gaps again, mark, remove, unmark, and continue. And you see the big drawback with this collector. It's fragmentation. You see all these gaps here, right? And this is the very simple idea to have every object one cell. This is not the case, as you know. If I would have objects that take 3 or 4 cells, then it will be harder and harder to find these cells in the heap, right? This is the big problem with this garbage collector, fragmentation. So this is mark and sweep. This is all it does. It works. It's very easy because you don't have to move stuff around. The problem is if you have larger objects, it's really hard to find space over time. Okay, that leads me to moving collectors, because we have 2 different kinds of moving collectors. If we start with the compacting collector, it's mark and compact. It's the same thing that we saw before with one additional step now. Instead of unmarking and then just continue, we do a compact. So that means we will see the same thing. I just started already because we don't have that much time. Once it stops, it marks the live cells, it unmarks, and then it frees the dead ones, it unmarks, and then it will compact all the live cells to the left side. You will see that. And that's the moving part. Now, unmark, compact, go again, right? Which makes sense, because now if we have bigger objects, no problem, right? But we have to move stuff around, live objects. And you can already imagine, if you think about the beginning, we saw the references pointing to these objects in the heap. Now I move the live objects, so I have to update all the references, because suddenly they are at a different memory location in the heap, right? That's the problem with this collector, because with all the moving collectors, because updating references is not easy, because these are live references. And the other one is we need some headroom at the end to be able to move stuff around, right? So this is another problem. So we will lose a little bit of memory. And that leads me to the next one, which is the copy collector, right? It's mark and copy. And you will see this looks totally different. Now we have 2 different spaces. It's the from space and the to space. In principle now, each of these spaces behaves like we saw before, but we don't do any compaction here, because that's the nice thing with this collector. It's automatically compacting. And I will just start it. You will see what happens. We just go from the left side. We fill that up like we saw before. Then we mark it. And instead of unmarked and free, we just copy all the live objects to the to space. And you will see the spaces will toggle now. Toggle, mark, move over to the other one, automatically compacted in this case. And then we fill up this space, and then we do the same again to the other side. You see already the advantage. It's always compacting by copying, right? Which is very smart, because then once we copied the live objects to the other space, we can just clean the whole area, because we know it's nothing live in there anymore, right? That's quite cool. Comes with 2 drawbacks. You might already have an idea. First thing is, which is obvious, we need twice the amount of memory, because we have to always have to be able to copy the whole heap in worst case. The other problem is, if we have large objects or even objects that are just older, right? They stick around for a long time. That means you have to copy them every time. And copy objects means moving references around, right? Updating references takes time. So the problem is long-living objects and twice as much memory. This is for the copy collector. But still, very basic principle. And if you understand that, you will also understand the next one, which is more complex. It's the so-called generational collector. All the collectors that we saw right now, this is just one generation, right? We allocate, we mark, we free, we remove, done. So multi-generational collectors work differently, because there's the so-called weak generational hypothesis, and that means most objects die young. This is not only for Java, this is for all languages, right? So that means you allocate objects, and most of them will directly die after you use them, right? Everything that is used in a method, for example, every object that you allocate or create new in Java in a method, once the method will return the value, all the objects are dead. So you can imagine, we have a lot of objects that will be allocated and die fast, and this is the graph to that thesis. That means, you see on the left side, very short-living. Most of the objects are short-living. Then we have a few medium-living objects, and then we have just very low amount of objects that live for a long time, right? So if we shape the heap according to this hypothesis, then it will look like this. We use the Eden space, so-called Eden, in the JVM for the really short-living objects. Then we have the so-called survivor spaces, and you already see this is a copy collector, right? And then we have the to-nerd space, and this is the old generation. That is stuff that survived a specific amount of garbage collection cycles. So that means we start allocating in the yellow one. It's small because the objects will die young, so only a few objects have to be copied to the survivor spaces. Then we copy them for some time. If they survived, for example, in my example, if they survived 3 iterations, I will move them to the old generation, to the to-nerd space. The advantage here is you see the to-nerd space, the old space, is very big. So garbage collection in this space will take some time before we get there. That's the big advantage here. So that means we have the young generation, which is Eden and the survivor spaces on the left side, and then we have the old generation, which is the blue part on the right side. If we talk about collections, if someone talks about a minor collection, always means Eden and survivor. It's only the young generation, always. This is minor collection. Major collection is only the old generation, right? And then we have full collection, that's both. Because people sometimes mess up full and major collection. So minor collection, young generation, major collection, old generation, full collection, both. That's the idea. And again, I have a demo, and this will take some time. You will see how it works. I allocate in the yellow part. If it fills up, I do a garbage collection. All the live objects will be copied to the survivor space. And then from the survivor spaces, we see when they fill up, moving around, and then when they are old enough, they will be promoted to the old generation. And then we will move through the whole old generation until we get to the final really garbage collection on the old generation. In this case, it's a full collection. Let's see how it works. And it's, I have some fast forward because it takes some time. You see, we mark it, we copy it over to the to space, and then we collect again. And because Eden is small, collection is fast, right? That's the main idea. So then we copy back, and if it reaches 3, every object that reaches 3 iterations, survived three garbage collection cycles, will then the next time be moved or promoted to the old generation. So now we do fast forward, and then you see how it works. And you see there's some kind of a wavefront going to the old generation, right? And until we reach the right side, we have to stop the world. Then we first mark in the old generation, and then we compact the old generation, and then we copy everything over from the young generation. You will see it happens now. Okay. Done. Mark it, free, compact, come on, and then move everything from the young generation. So this is how a generational collector works in general. Then we start from scratch. Right? This is the idea behind a generational garbage collector. And this is quite good because it adapts to the natural behavior that we have with these objects die young, and with these iterations that survive, or with the object that survive the garbage collection cycles. I think it is 32, if I'm right, in the JDK. You have to survive 32 garbage collection cycles before you will be promoted to the old generation, right? Okay, this is a generational collector. Now you have an idea of the basic collectors, and like I said, this is the most simplest approach you can think of. I told you minor collections are only in the young generation, right? What happens if I have a reference from the old generation that points to the young one? Because when I do a collection in the young one, I don't know about references that are somewhere in the old generation, right? So like this. We have the roots, which is the stack frames, and then we have the young generation on the left. Now we decide to do a minor collection on the young generation. We have all these references pointing somewhere. We have stuff that points from the young to the old. That's fine because we do the collection in the young generation. We know, okay, there are references. That's good. These objects are live. But what if we have a reference that points from the old to the young? Because when the collector does the minor GC, it doesn't know that this cell is referenced by something outside of this area, right? So that's the problem. If the collector would just do it, the one with the question mark would be removed as dead, because the collector doesn't know that there is a reference. So to fix that problem, there's a so-called card table. It's also known as the remembered set. So you probably read about remembered sets if you read about garbage collection. This is the idea is there's a specific table which is optimized and that has the reference. It knows that there is a reference from the old generation to the young generation. And then the garbage collector knows, oh, there is one. So I mark also the one with the question mark as live because I know there is a reference. I know that from the card table or from the remembered set. It's just, there will be so many things I will talk about. So just remember remembered set, right? That is more than enough. It's just to make sure that you have this intergenerational references covered. So that was the complete easy part, because that's all stop the world. If we talk about concurrent collection, it's a different thing, because concurrency is hard, right? So if we talk about concurrent marking, right, we have to find the live objects. Concurrently means at the same time, the application is allocating memory, and also objects will die, and the collector should at the same time mark stuff that is live, remove stuff, and it should work somehow, right? So we have to figure out how that works. Concurrent marking is if we have the roots, which is the stack frame on the left, it has a reference to the objects on the heap. So it finds the first one and say, oh, I can reach it. And then it marks the one as, yes, this is live. Then it goes to the next one, says again, oh, I can reach it, mark it as live. But at the same time, suddenly, the allocator decides, oh, you know what? I just kill the reference and create a new one, right? But the collector was already at the first cell, so it doesn't know, right? So we just continue, and then at some point, this one will be removed by the collector because it doesn't know that there is a new reference. It wasn't there when he checked the first reference. That's the problem. How can we solve that? Right? So then it does everything, and the problem is now it's collecting, it's freeing, and the cell is not marked. It means it will wipe it out. But in the meantime, we had the reference from the allocator. So there is a principle which is called barriers, Who knows about barriers, read and write barriers? Someone ever heard about it? Okay. So the idea is to make it as simple as possible. You have some piece of code. Every time you read a memory cell or you write to a memory cell, this code will be executed. That's the barrier where you have to go over before you can actually read or write. That's the idea. So you can implement it on each memory cell if you like. And they're different. And like I said, it's some piece of code that will be executed. They are used to keep track of intergenerational stuff that it leads too far. If we go into details, it's also used to synchronize between the mutator and the allocator, or the collector. The mutator is the allocator in this case. And one thing you have to keep in mind, because if you compare reading memory to writing memory, then the ratio is probably 8 to 2. So it's way more reading than writing into memory. That means if you implement the read barrier, this should be very efficient because it will be triggered so often, right? It has to be very efficient to don't bring the performance down. All right, if we go back to the same example, so collector is starting from the left side, finding the first reference, mark it, okay, I can reach it, it's live, go to the next one. Now the allocator steps in and says, okay, I remove the reference, and here we see the write barrier. Now the allocator comes, removes the reference, and creates a new one. And the piece of code in this example would say in the write barrier, when you remove the reference, every cell it was pointing to will be marked as reachable. That's the piece of code that will be executed in this case in the write barrier. That's the idea, right? So when the allocator steps in, removes the barrier, the reference here, the red one, it automatically will mark the other one as reachable, not as live yet, right? So then the collector can just go on. Once he finishes everything marking live, there's the so-called remarking phase, right? So the collector now goes and it stops the world shortly and just finds all these new reachable references and mark it as live. And then it's made sure that this reference won't be removed to this object. So this is so-called snapshot at the beginning. That means you implement a write barrier, and once the allocator is starting to writing to something, you can decide whatever it should do. In this case, it just says, every time you remove a reference, mark the old one still as reachable to make sure you can see it. But this is up to you how you implement it. That's concurrent marking. Concurrent copying is even more complex. So if we take a look at stop the world, normal thing, right? So we fill up the heap, it's full, now we stop the world, no thread is doing anything. We just take the object that we would like to copy, we stop it, the world, then we take the object and copy it to the new position, right? We implement a forwarding header on the object. That means every reference that points to this old one will now update it to the new one. That's how it works. And once you updated all the references, when you moved it, then you can remove the old object and continue, right? That's pretty simple, because this is really, because we stop the world, nobody's doing anything when we update all the references. It looks totally different if we do that without stopping the world. So we do the same. We start taking the object, copy it to the new location in memory, and suddenly both objects are reachable. They are both lying around in the memory. That means suddenly you can start updating references, right? But even the old ones will be reachable and the new ones will be reachable. That means threads can now access both objects at the same time. And what's the right one? You can't really tell, right? So that's the problem here. So we have to find a way to somehow make sure that we can copy an object even if threads are accessing the memory, right? Which is a tricky thing. And there are different solutions, and I will just tell you one. And this is the so-called Brooks pointer. So before we copy, we install a forwarding pointer in the original object. And the forwarding pointer points to the same object, to itself, right? So if we now copy this object, there's nothing pointing to the forwarding pointer in the copy here. And with this, nobody knows about that one, because it's not reachable. It's the header, the reference is not there, and it's pointing to itself, so that this is safe. That's no problem at all. And now what we do is we just point this forwarding pointer to the new header. And now all references that go through this one, and even if they go to that, they all go to the right object. And then we can update all the references over time, it's no problem. Right? So this is, because this header on the left side, the forwarding, this is visible, but the other one, because nothing is pointing to it, it's not a problem here. It's a little bit tricky to understand, and believe me, it gets more complex. This is just the simple stuff. So when you updated everything, then you can remove the original object and then free the memory. That's the idea. So you see, it's really tricky to copy stuff around in memory that is in use, because you have to make sure that everything still works without stopping the world. By the way, stopping the world just means the JVM has so-called save points, and that means when you move into a save point, that means all threads are in a safe state, and then the JVM can stop the complete threading thing and can do garbage collection. This is a stop the world, because nothing else except garbage collection is working then. If we talk about concurrent garbage collection, we don't have stop the world, really. We just do it all at the same time, and that's really tricky, as you can already imagine. So if we now take a look at the collectors in the JVM, we have different ones. We have serial collector, still one of the defaults, right? So because the original slide deck had 270 slides, which doesn't really fit in 45 minutes, I created this more compact views of each collector, so sorry for that. You see on the left side, it's available in all JDKs, it's not concurrent, no parallel, it's generational. All the collectors are generational except one, and we will come to that. Heap sizes for small and medium heap sizes, pause times more longer than shorter. It has a more or less low throughput. Latency is higher. CPU overhead is quite low. Right? The idea is you have, for example, 10 threads working on your application. Then you stop the world. Then you have one thread doing the garbage collection. Once it's done, you continue with your 10 threads for the application. This is how the serial collector works, right, in principle. And it's good when you have a single core system with a small heap. Small means smaller than 4 gigabytes. And you have no pause time requirements. It's quite a good collector. So if you work, for example, with Docker containers, who's working with containers here? Yeah. Who's working with small containers on very small nodes? 1, 2, OK? If you do that, and your memory is below 1.8 gigabytes, and you only have one CPU, then, and you don't specify the garbage collector, you will get this one, right? So it's not G1. You have to keep that in mind. The JVM will automatically select this collector if you either have only one CPU or if you have less than 1.8 gigabytes of memory. This is, you can select another one, but if you don't select it, you don't get G1, you get this one. Just be aware of that. It doesn't mean this is a bad collector, right? So this is, it's good. For this use cases, it's quite a good collector, but just to keep that in mind, it will be selected automatically. Then we have the parallel collector, also quite old one. To make it very simple, remember I told you we have 10 threads working on the application. We stop the world, and now we have 10 threads doing the garbage collection. And then we continue with the same 10 threads for the application. So you can already see the advantage here, because if we have lots of threads working on the garbage collection at the same time, garbage collection will be shorter. And this is directly related to throughput. Throughput means time you spend in the application versus time you spend in garbage collection. And if you spend just very small amount of time in garbage collection, the throughput is quite high. That's the reason why this is called the throughput collector. And it's still a really good collector, especially when you do batch processing, scientific computing, data analysis. If you need peak performance, it's just good, but you have still stop the world pauses. Have to keep that in mind, right? And the CPU overhead is also low. So it's a quite good collector if you're aiming for throughput. Okay. So that was the default garbage collector from JDK 5 to 7. Oh, by the way, who's using, I don't want to ask, but who's using below JDK 8 in production here? This is very good. Who's using JDK 8? Wow. JDK 11. Okay, 17. Cool. 21. The fearless, 23. Early access. Okay. Good. But that's good. You're a really good audience. Well done. Then there's this one. Concurrent mark and sweep. And remember, I showed you the generational garbage collector. This is more or less exactly how it looks like, but this is concurrently working. But the Eden, the survivor spaces, and the to-nerd space, they look like this. We have these different regions, right, the bigger ones. This one is deprecated, so that means if you, on JDK 17 already, you can't even select it anymore. That was removed in JDK 14, it was deprecated in JDK 9. And it doesn't mean it's a bad collector. It was in the JDK from JDK 1.4 to 13, and it's partially concurrent, so not completely. And it was built for if you have response time. If the response time is more important than the throughput, then this was a very good collector. And if the pause times must be kept below 1 second, then it was quite good. But as I said, and as I saw, most of you on 17 and 21, you can't even select it anymore. And this isn't really a problem because we have something that replaces that one, if my clicker works. It doesn't. It was deprecated as of JDK 19 and removed in JDK 14, and the replacement for that is G1, garbage first. And this is a totally different collector. You know, I showed you these different areas that we have with the to-nerd space quite big and the survivor spaces and all that. The difference here is this is a so-called, and was the first one, so-called region-based collector. So we have these regions. This is the heap. And on the left side, you see if the heap is smaller than 4 gigabytes, each of the regions is 1 megabyte. And then this grows with the heap size. So if it's more than 64 gigabytes, each of these regions is 32 megabytes. And they can grow, but they can't shrink. So if the JVM figures out, oh, the region size doesn't really fit, it can increase it, but it won't go back to the smaller ones. And the idea here is that, let me try again. It doesn't work, okay. Do it this way. Instead of having fixed regions, we just take the first one, and when we allocate, this is now the Eden space, right? So we just allocate in this area, in this region, and then we continue. If it's filled up, then we take the next one, right? We don't do garbage collection yet. We just take the next one, and so on, until we reach a specific ratio, right, between young and old generation here. So let's say we reached it, and at this point, we have to figure out, okay, which of these regions has the most garbage, has the less live objects in there. We take this, and it's, for example, these 2 regions there, and we copy the stuff from these 2 regions in a new one. It's the survivor space now. And then we can free the old ones, because they're not used anymore. And so we continue, right? So it looks, after some time, it looks like this. We have the survivor spaces. If we have lots of survivor spaces, we copy them around, and then at some point, if the survivor spaces are filled up, they become a to-nerd region. And then this continues, and then in the end, it can look like this. And even for huge objects, we have so-called humongous regions, right? The definition is here on the right side. Their region size, it's bigger than half of the region size, an object, then it gets a humongous region. These are not going through Eden, Survivor, and to-nerd. They are just staying there as they are. The advantage with the region-based collector is you can already see, we always find some free spaces here. So it's not really the problem that we have a fixed size for Eden, a fixed size for the survivor spaces, and for the to-nerd space. And we only do the garbage collection in these regions that are filled up with the most region first. That's the idea, right? So this is the G1 collector. In principle, the same as we saw with the CMS collector, right? So who's actively choosing a garbage collector for production here? Yeah, that's what I thought. Most of you just trust, right? Just use the default, this one, for all of you. Because nobody was in, this is since JDK 8, the default one. So that means all of you use G1, most of you. I think it was 3 people. And that just means they did a good job because it seems to work somehow, right? Doesn't mean it's the perfect collector yet for you, but at least you seem to be happy. And as you can see, it's made for large size enterprise system and responsive in medium to large heaps. So that's quite okay. It's not really good with small heaps. So if you go to this, the people who pointed up their hands when I asked for the small nodes in containers, with small amount of memory, don't use G1. use the serial one. It's quite good. So this is not good for small heaps, right? Okay. So yeah, that's the default collector since JDK 9 onwards. I said JDK 8, right? I thought it's also in JDK 8. Who knows that one? Epsilon. No one? Or one? That's the so-called no collector collector. But it doesn't do anything. It's not garbage collecting at all. Okay, why is it a collector then, right? Well, you can imagine if you would like to test the application performance, right? Only your application. Then usually if you do that, you can run the best test suite. It will always also have garbage collection when you test it, right? Because it will do garbage collection, but you have any influence on the garbage collection. Neither when it will happen, what size the heap is, when it does it, and all that. So garbage collection just happens, and you measure your application performance including garbage collection. If you are keen on measuring the application code itself only, this is the collector to use. But be aware, I told you, it doesn't do any garbage collection. The heap will fill up, and when it's full, you get an out-of-memory exception. So that means you really have to know how to use it and how much memory are you using in your application. But you can monitor that before, and then you can do some test runs. If you run very small microservices, where you exactly know how much memory they use, this is the most performant way of doing it, because you don't have any garbage collection. That's the reason why it's in there. If you really need the last drop of latency improvements or throughput improvements, this is your collector. But it's only available in OpenJDK. Someone using OpenJ9 here from IBM? Okay. Because they have similar collectors, but they have different names, and they work a little bit different because it's a different JVM, and they don't have Epsilon. Then we have Shenandoah. Everybody knows that? No? This is a collector that was invented by Red Hat. And now I have to ask, who is using Oracle JDK here? I don't mean Oracle OpenJDK, Oracle JDK with a subscription. Very good, because you don't get this one. I don't know the exact reason, probably because it's not invented by Oracle, so it's not supported. But if you have OpenJDK, it's in all OpenJDK distributions. Just the Oracle one doesn't have it. This is a fully concurrent collector. That means, yes, it still has, even the fully concurrent collectors have very small pauses, but they are so small that you can just ignore them. That means it's fully concurrent. This is the only non-generational collector in the JVM. Every collector else is a generational collector. This one only has one generation, right? And that means it could be even faster. And I know that they started working on that, but I'm not sure if it will ever make it, the generational Shenandoah. But at the moment, this is the one that is available. It's quite good for large-scale systems. They guarantee you a response time. I think it will be below 10 milliseconds, if I'm right. And so that's guaranteed. The maximum response time is, or pause time is 10 milliseconds. And it's using very large heaps. It's for highly concurrent applications, large-scale systems, and if you have latency-sensitive applications. So like I said, it's not available in Oracle JDK. You have a little bit of a reduced throughput that is for all the concurrent collectors. And the reason is simple. I'm going back to the 10 threads. I have 10 threads running on my application. We have a concurrent collector. That means I don't stop the world for garbage collection. That means these 10 threads running the application, and they do the garbage collection at the same time. That means the amount of performance that is available for your application is reduced, right? Because we have to do garbage collection at the same time. This is for all concurrent collectors, also for ZGC. And this uses a read barrier concept. It's called load reference barrier in this case. And yeah, like I said, they have a little bit reduced throughput. That leads me to ZGC. Someone using ZGC from the people that pointed up? No? Okay, that's the newest one in OpenJDK. And it's very similar to G1, how it looks like. It has regions. All these new collectors have regions, also Shenandoah. So we have young generations, and then if they age, they become old. Like, there is no survivor space here. It's only young and old generation. They will be promoted, and then it's an old generation region. These are not really separated regions, so that it looks like this, right? We have young and old ones. This is how ZGC is organized. So they got rid of the survivor spaces, and aging means surviving garbage collection cycles, right? This is the idea. So I don't have lots of details on that one because I will come to another one, and this is just more or less a copy of that. So this is also fully concurrent. You see it has a more CPU overhead, 10 to 20%, really depends. Netflix recently did a test. They switched completely to ZGC, and they saw a drop in performance of 3%, right, for their application. And this really depends on your application. But keep in mind, if you go to this collector, to a concurrent collector, it will reduce performance, even if it's just 3%. That means if you would aim for the same performance for your application, means you have to spend, for this 3%, you have to spend more money in nodes or whatever on your cluster to get to the same performance as before, right? So it's just to keep that in mind. It doesn't come for free. It's made for very large heaps. We talk about terabytes here, and very low latency sensitive applications. So that means we have, I think guaranteed, that's not really guaranteed, but it's usually around 3 milliseconds, the pause times, which is more or less nothing. You can more or less ignore it. It's made for large-scale systems, highly concurrent applications. At the moment, it's still non-generational, but with JDK 23, it will switch to generational, right? At the moment, you have to switch it on like this, with Z generational, then you will get the generational ZGC. And in the future, you don't have to. The old non-generational one is already deprecated, so it will go away anyway. So you won't have to do anything if you use it. It will be generational. It will probably become the default collector in the future at some point. Not in JDK 23, but maybe later on, we don't know. And like I said, the non-generational version will be deprecated. That leads me to the last one, which is C4, which means concurrent continuous compacting collector, which was invented by Azul more than, I don't know, 12 years ago or even longer. And that's why I didn't spend a lot of time on ZGC, because ZGC is more or less really a copy of this collector. It's exactly the same. The non-generation is exactly the same thing. They have different names internally, but it's technically no difference. So everything I say now also belongs to ZGC. This is only available in Azul Zing, which is our own JVM. It uses loaded value barriers everywhere, so that's a read barrier. And if I'm right, in ZGC, they name it colored pointers. Right? It's the same thing. So technically, no difference. And if you work on Linux, who's using Linux here in production? OK, you probably know. Transparent huge pages will help, because this is bound to the region size is bound to the memory pages in the operating system. So in Linux, you can define that by using transparent huge pages and enable it, and then you have the best performance. If we see how this works in the marking phase, and that's different from the other ones that I told you, it's quite interesting. Because we have the GC threads on the left side, they start to find the references, the live objects on the heap, by following the references, and then they start marking stuff, right? OK, this is live, and then the lower right one was not really referenced yet. So if now the allocator, the application thread, starts allocating this memory cell, the collector doesn't know. Instead, what will happen will, there is a LVB, the loaded value barrier, or read barrier, or colored pointer, whatever you name it. And this piece of code will make sure that this memory cell will be marked as live from the allocator, not from the collector. And then it will tell the collector, like, you know what? I marked this cell. And then the collector knows, oh, OK. So if I do the collection, I have to keep that in mind. So the difference here is that the allocator and the collector work hand in hand. Both of them can mark objects live. That's different from the other versions, because in the other versions, the application threads or the allocator doesn't do anything. It just allocates stuff. It hits a write barrier, and then something will be marked as reachable, but not really marked as live. In this case, it will be marked as live by the allocation thread, by the loaded value barrier in this case. And that makes it possible that once a cell is marked, it doesn't have to be checked again by the collector, right? You only have to check it once. So it saves a lot of time. And you maybe saw there was something called test and jump. So that means when the allocator gets the memory cell, it tests it. Is it a reference? It's not, because it's free. And then it tries, if it's a reference, it tries to jump. Like, if it's a reference, let's see if I can reach it. And then it marks it. And this is important if we come to remapping, because this is now the same that I showed you when we copy objects on the heap concurrently. Then I told you there is this forwarding pointer, the Brooks pointer thing. In C4 and ZGC, it works differently. So when we start copy stuff, we copy the headers, right, or the objects. And instead of putting the forwarding information in the object header, we put it off heap, also ZGC, in a specific place. It's always the same place. And that leads to the fact that when we updated all the references and suddenly the allocator starts referencing the old object here, right? It will first of all do the test and jump. It will see, oh, that's my object. Is it a reference? Oh, it's not reachable. It will look it up in this forwarding table off heap, and then it will update the reference and also the pointers, and everything's done. So this is a little bit different here, because on the other objects, it's stored in the original object header. That means you have to keep the original object in memory as long as all the references are not updated. In the lower case, you don't have to, because the forwarding information, it's copied to off-heap space. That means as soon as we move the object, we can remove the old one, because every access will go through the loaded value barrier, which means look it up. Can you reach it? No, then look it up in the forwarding table. And this is always reachable. So this is the so-called quick release, because the underlying physical memory can directly be released, which is faster. It sounds like tiny pieces when you look to performance, but it makes a huge difference, because this is working concurrently all the time, right? So you have a small impact on each object, which sums up to a huge impact if you take it to the whole system. And the other system has to update everything before it can really remove the old object from the memory. All right, so you have to choose it if response time is high priority. The same for ZGC, right? So the customer with the biggest heap that we have has a 21 terabyte heap. When I heard that the first time, I was like, 21 terabyte or gigabyte? No, terabyte. So I was just thinking about the machine, how big it must be to have 21 terabyte of heap just for Java, and then we need also additional stuff in memory. So this is for low latency systems, large-scale systems, highly concurrent applications. It's only available in Linux at the moment. And this is only available in Azul Zing, in our own JVM. The only difference to ZGC is that we are still faster because we don't have the OpenJDK compiler. We have our own compiler. And that is faster than the OpenJDK compiler, so we don't have the problem with the drop-in performance that we have with all the other concurrent collectors. So the question is which one to choose. We have all these different ones. And we have three essential criteria here. First of all, if you aim for throughput, right, time that you spent in application versus time you spent in garbage collection, then there's latency, right? That's the responsiveness of your application, affected by GC pauses, and we have resource usage. So this is how much memory do I need for the garbage collector and so on. So it's good that it's only three criteria. The bad part is it's 2 out of 3. So it's your choice. Oh, I would like to have very low latency and I would love to have very high throughput. Awesome, but you will get very big resource usage. Sorry. If you would like to have low resource usage and very high throughput, yeah, you can get it, but sorry, latency won't be low. This is the stuff you have to keep in mind when you choose a garbage collector, right? It's not like, oh, I would like to have everything. It doesn't work, right? So to make it easier, you can use this diagram, so which is the pause times on the upper arrow, pause times increasing to the right, right? So this is the stop the world pauses. The runtime overhead is increasing to the left, the lower arrow. So now you can choose. You see already G1 and CMS, it's quite a good choice, and which is the reason why most of you are happy with this one. If you really aim for very low pause times, but you can live with the overhead, then ZGC or C4 or Shenandoah might be a good choice. If you really look for very low resource usage and no runtime overhead, then parallel and serial is a good choice. Right? So you see, it really depends on your application, and there's no general rule that tells you this is the perfect garbage collector for everything. Know your application, monitor it, then choose the right collector and the heap size. Right? This is the advice. There's an overview where you can see all of the garbage collectors with their heap size, performance, CPU, overhead, and so on. And I guess the slides will be provided of the conference. I think so. So you can look it up. And as you can see, Epsilon doesn't have anything because it's not a collector at all. And with this, I'm done. So if you have questions.